Hey guys, Mrs. T here. This is another video. This one is about residual plots. So up to this stage in the topic, we have used R, Pearson's correlation coefficient, and R squared, the coefficient of determination, to act as a measure and determine how well a linear model fits a set of data. Now another step to determine whether a linear model fits the data is to look at the residuals or analyze them. So before we talk about analyzing residuals, we need to know what a residual is. So for every point of data on a scatter plot, every point has a residual, and that residual is the observed y value of the data point minus the predicted y value of that data point. So what does that mean? The y observed is the actual data point that you've plotted on the axis, on the scale. And the y predicted, that's the y value of the predicted data point for that given x value of that particular bit of data. So you've got these data points scattered across your scatter plot, and they're at different x coordinates. And when you've devised the least squares regression line for that particular set of data, that equation of that least squares regression line is giving you a best fit relationship between y and x. So that line is predicting what y should be when you're given an x, based on a best fit set of maths that the calculator's done for you. That might not necessarily be what the actual data point is, because the predicted line, the linear regression line, is trying to fit the relationship as best it can overall, not every single data point by itself. Okay, so the y predicted is the y value for each data point, given an x value plugged into the least squares regression line devised for that data. Okay, so that is quite a complex point to deal with there. Hopefully it's sorted out a little bit when we do an example below. One thing to notice is that because you are taking away the predicted from the observed y value, if that residual is a positive number, it indicates that the data point is actually laying above the regression line. If the residual is negative, then it indicates that the data point is lying below the regression line. So now that we've talked about what a residual is, the thing that we're going to be looking at is residual plots. This is going to offer us a way to analyze the residuals and tell whether a linear relationship is applicable to the data. So a residual plot is a scatter plot of the x values of the data versus the residuals that you found for the data. So you're going to use the same x numbers for the data, but instead of the y data, you're actually going to plot the residuals, the differences in the y instead, compared to the predicted line. Basically, you can think of residual plot as it's just a graph that shows the difference between the actual data point and what the data point is predicted to be according to the least squares regression line. So now it's time for the example. There's a lot of language there. I'm just giving you like the specific, definitions of these things because, well, you have to know them or at least be exposed to them. When we see the example, hopefully it clears up a little bit and it's not too bad, okay? So let's look at this data. You've got X data and Y data, 3, 4, 6, 9, 11, and then the accompanying Y data is 7, 4, 10, 11, 20. Firstly, we need to find the equation of the least squares regression line for that data, find the residuals for that data, so this is the new part, and then draw a residual plot for the data, which is another new part. So a lot of this I've already set up because I just want to show you the new portion, okay? So where do I enter data on the calculator? As always, stat, one edit, enter the data into L1 and L2, L1 being X, L2 being Y data. Then use stat, move over to the right and select the calc tab, press for lin reg, and you'll find once you calculate the lin reg, you're following. Lin reg will come up with A is equal to this for that particular set of data. B is this for that particular set of data. and r and r squared are quite high. So according to r and r squared, a linear relationship is appropriate. It's not absolutely perfect, but it's appropriate for this. And so from our previous video, talking about the least squares regression line, this would be the equation of the least squares regression line. So here we have a link between the y coordinate of the data and the x coordinate of the data. This is a rule that's going to predict what y is going to be for a given x. That is different to what we actually find in the observed data, because here, for an x of 3, we find 7. That might not be what is predicted according to this equation. So what we are actually finding is the y predicted first. We can't find the residual yet, because it's the difference between the y observed and the y predicted. We know what the y observed is, it's this. We need to know what the y predicted is using this equation here. So we need to substitute the known x into the equation to work out what the predicted y is. Y is going to be 1.6106 times by the x value that we know is 3, take 0.2301, y comes to, go to the calculator, sorry, 1.6106 times by 3, take 0.2301, that comes to 4.6017. Okay, that allows us to work out what the residual is. Resid is going to be the y observed, which was 7, the actual data point, y value minus the predicted, 4.6017. 7 minus 4.6017, that comes to 2.3983. So that's our residual. Okay, so we need to go through and complete the table for the rest of it. So y is going to be 1.6106 times by 4 this time, minus 0.2301, comes to 6.2123. Residual is going to be the y observed, 4, minus 6.2123, 4 minus second answer, negative 2.2123, so that's a negative residual. So that point must have lay under the least squares regression line when drawn on the scatter plot. Next, keep going. 1.6106 times by 6, take 0.2301, 9.4335, residual. This is a long process, but lucky for you, there's a way to do it with a calculator. So y observed, 10, take 9.4335, 0.5665. So that's telling me the difference between the data point and the least squares regression line was much smaller there. So the data point would have been close to the least squares regression line. Next, 1.6106 times by 9, take 0.2301, that's 14.2653, residual, the observed was 11, take away the answer that I just got, negative 3.2653, so that was a bit further away from the least squares regression line. Last one. 1.6106 times by 11, take 0.2301. So that y predicted is 17.4865. Residual is then 20 minus that answer, 2.5135. So we've worked out the residuals. This is a new thing to you, the idea of residuals, and that's telling you how far in the y direction the data points lay from the least squares regression line. Let's see if that actually is the case according to the data. Here I've graphed that data above. 3, 7, 3, 7, 4, 4, 4, 4, 6, 10, 6, 10, 9, 11, 9, 11, 11, 20, 11, 20. So that's the data. Here I've drawn a graph of the least squares regression line according to the lin-reg function from the calculator. And as you can see, this residual was positive 2.3983. And as you can see, here on the least squares regression line, the data point is above it. It's a positive residual. It's above it by 2.3983. The next residual indicates that this jump from the least squares regression line down to the data point is negative 2.2123. It's below. The next one, how we spoke about, the residual was much smaller, much closer. You can see this dot is above, so it's a positive residual, but much closer to the line. Here we've got a further away one. It's down by 3. Does that fit? Well, the line crosses here just above 14, and the dot is actually at 11. So yeah, it's a little bit over 3 below the least squares regression line. And here we've got another far one, 2.5135. So hopefully you can see that the residuals represent how far above or below the least squares regression line the data points lay. Now, to draw a residual plot, all you are doing is plotting the same x's from the data, that serves as your x-axis, and the y-axis is going to be the residuals instead of the y data. So when x was 3, the residual was 2.3983, 2.3983, so it's going to be like somewhere there. Oh, that's in the wrong place. When x was 3, 2.3983, so somewhere there. My bad. When x was 4, the residual was negative 2.2123. So when x was 4, negative 2 point, so less than somewhere there. These aren't exact, it's just to illustrate. When x was 6, the residual was 0.5665. 0.56, somewhere there, just a bit over 0.5. When x was 9, the residual was negative 3.2653, negative 3.26, somewhere here. And lastly, when x was 11, the residual was 2.5135, so 2.5, just a little bit over 2.5. So that is the residual plot that is representing the y distance above or below the least squares regression line that the data points actually sit at. So you can see here that this data point was quite a bit, like 2 and a bit above the least squares regression line. This was 2 and a bit below. This one was only a little bit over half above the least squares regression line. This was quite far, over 3 below the least squares regression line. And this one was 2.5 over the least squares regression line. So that is a quick overview of what residuals are and what a residual plot is. The next video should be about how you do this process, because obviously that takes forever. You won't be able to do that in a test situation. How you do that with a calculator and speed it up. And then after that is analyzing, well, what do I actually get out of this? Because we said that residual plots and analyzing them allows you to decide whether a linear relationship is appropriate for your data. So hopefully that helps you out, and I'll see you in the next video.